started to look at table 8.2, we said that if x of n has got a DFT x of k, x1 of n and x2 of n both have got the corresponding periodic sequences, both have to have the same length n. Okay, so x1 of n has got the DFT coefficients x of k. This is a n-point sequence. Okay, similarly, this for the same length, x2 of n mapping to x2 of k. This should be x1 of k. Okay, so these are the conditions under which we are deriving these results, and we said that the property of linearity can easily be verified because this is a linear transformation. So if you scale the input sequence, the corresponding DFT coefficients will also get scaled. Now, the first relationship that we discussed and obtained is the circular shift operation. Okay. Now, we always want to go back and look at the representation that we have for the signal, and we say that, okay, what is the corresponding DFS relationship? And once we have the DFS relationship, then we can easily establish the corresponding DFT relationship. So look at the for obtaining the circular shift. So property number 5, this what we have derived here is property number 5. So x of n giving x of k. Now we know the following property for the DFS. X tilde of n minus m has got a DFS relationship which is given by e power minus j 2 pi by n k m x tilde of k. Okay, so this is the DFS relationship. Okay, so this is the DFS relationship. I'm going to write it in a different color so that you can always refer to this. And now from here we get the corresponding DFT relationship. Remember, we're looking at one period. Any argument of x tilde of n has to be interpreted modulo n. Okay, so that's the first thing. So x will be interpreted modulo n. So let us capture that with the following. Okay, so x tilde of n becomes x of n minus m modulo n. The scale factors identical. The x tilde of k, one period, will be x of k. So you can see how, if you are familiar with the properties of DFS, the circular shift property of the DFT can be easily obtained, and we know that Wn is a representation e power minus j 2 pi by n. So we can write down the circular shift of the DFT n minus m interpreted modulo n is given by Wn km times x of k. This is the circular shift property. Okay, so we can tick off the circular shift property, and the other property that we had derived is the duality property. Okay, that's another very important property which we said that exists for the DFS, it exists for the DFT. Okay, so these are the two relationships that and we had derived the duality property. So let me label that as number 4. That is the duality property. Okay, this is the circular shift of the time domain sequence, shift in time. Okay, and the duality property says that if I feed, again we'll write down the DFS relationship, if I feed x tilde of n to the forward relationship, and then what I will get is a scale factor times the input sequence, but with a time shift, right? The time reversal. Okay, there is a time reversal as well as this representation. Now, how do we translate this into the corresponding duality relationship for the DFT? X of n will produce, if you feed it to the forward transformation, will give you n times, this is x tilde, this is x tilde, okay, will give you n times x minus k has to be interpreted modulo n, and that is exactly what we will do. We will take minus k and interpret it modulo n, and this is the duality relationship. So what we saw here as the duality relationship is exactly what we have. In the same manner, I would like you to verify the following results. Okay, I would like you to verify. Again, very simple. Go back to the DFS relationship, obtain the corresponding DFT expressions. Wherever there is an index that can go out of the range 0 to n minus 1, you have to interpret it modulo n. Verify property number 6, which is a circular shift in frequency. Shift in frequency will produce for you a time domain sequence which is multiplied by a complex phase term. Okay, so this is a property that I would like you to verify. Again, use the properties that we are already familiar with. All right. So now what we are going to do is to look at the derivation of one of the important properties that again is present in the DFS. We want to be able to understand and apply it in the case of the DFT. Okay, so that is property number 7, the circular convolution property. So let's write it down. Okay, let's write it down. So the summation of m equal to 0 through n minus 1, x1 of m, x2 of n minus m, this has to be interpreted modulo n. This is the circular or the circular convolution of the two sequences x1 of n and x2 of n. So we can write this as x1 of n circular convolution of n points. This is lowercase n of x2 of n. That's the expression that we have here. Want to relate it to the corresponding DFT coefficients. We will show that this is equal to the product of the DFT coefficients x1 and x2 of k. Okay, so this is the convolution property, periodic convolution property. Okay, let me write it down. So this is periodic convolution. This is also property number 7. Property number 7. Okay, so let me indicate property number 7 is what we have. That's what we are going to be verifying. Okay, so first thing is for DFS, for the periodic signal x tilde of n with periodic DFS coefficients x1 of n with x1 tilde of k and x2 tilde of n with DFS coefficients x2 tilde of k. What is the periodic convolution property for these two sequences? Summation m equal to 0 through n minus 1, x1 tilde of m, x2 tilde of n minus m. We know that this has got the corresponding DFS relationship given by x1 tilde of k and this as x2 tilde of k. Okay, So now write down the corresponding representation for if we want to look at the corresponding relationship for the DFT, then we are going to write down the following result. M equal to 0 through n minus 1. This one becomes x1 of m. This one becomes x2, but remember the index n minus m may go outside the range 0 to n minus 1. So whatever is its value, it has to be interpreted modulo n. This will give us the periodic convolution or the circular convolution between x1 of n. This is the circular convolution of x1 of n, an n-point circular convolution with x2 of n, and this is related to the corresponding relationship. This is the DFT of the first sequence multiplied by the DFT of the second sequence. Okay, we know how periodic convolution works. Periodic convolution, okay, we are looking at two endpoint sequences producing an endpoint sequence as the output. So this is a important aspect that we want to always emphasize, want to always keep in mind, and also be able to apply it correctly. So basically, we're looking at the periodic convolution property. Periodic convolution in time, okay, this will produce for us the product of the DFS coefficients. The product of the DFT coefficients. It's also DFS coefficients, but we are now looking at the DFT coefficients. So again, this is a property that is very important that we have proved, and we will utilize this result. In the same manner, you can do, so this is convolution. Okay, this is circular convolution. Okay, now multiplication in time. If I multiply two sequences, two endpoint sequences, what will happen? Just like we had for the DFS, when you multiply one period of two periodic sequences, then what you will get is the circular convolution of the DFS coefficients. In the same manner, we now have a periodic circular convolution of the DFT coefficients, again identical. So I will request you to verify number 8 also to be verified. This is the property of multiplication in time. Multiplication in time. So with this, I'm confident that you will be able to understand and look at the DFT. Always remember the corresponding relationship to the DFS, and anytime you have a index that is going outside the range 0 to n minus 1, then you must will have to interpret it correctly with a proper modulo representation. Now, I think just to get you a little bit more interested in the study of the DFT, let me capture for you the DFT matrix. Okay, the DFT matrix is given here. Okay, let me see if I can capture the entire DFT matrix. Okay, that's the DFT matrix. Okay, so this is the DFT matrix. This is what we denote as D subscript n. And we know that W subscript n is e power minus j 2 pi by n Kn. Okay, and we have the relationship, the uppercase x, which is the DFT coefficients, is Dn, the matrix, multiplied by the time domain sequence, endpoint sequence. Okay, so here are some important properties of DFT, of the DFT matrix. Properties of the DFT matrix. You can just look at the corresponding relationships or look at the expressions that are there in the left hand box and be able to write down. The first property that I would like you to verify is what is the expression for x of 0. X of 0 is the topmost DFT coefficient. So, that is basically the first row. Notice that it has all ones, and therefore, this is nothing but the summation of all the time domain coefficients, n equal to 0 to n minus 1 x of n. So, the first coefficient is always obtained as a summation. By the same token, if you did it on the inverse DFT transformation, x of 0 inverse DFT coefficients will be 1 by n summation k equal to 0 through n minus 1 x of k. Here again you get the sum of the DFT coefficients. There is a scale factor of 1 by n which is associated with the inverse matrix. Okay, another interesting property you will write down. What is x of n by 2? Okay. What I would like you to do is to go back and look at the expressions for what we have for x of n by 2, and x of n by 2, if you were to write it down, is summation n is equal to 0 through n minus 1 x of n w n. The value that we are going to be evaluating is n by 2 times n. Okay, this is the value of k. So this is what we are evaluating, and this is, we will write it as n. Okay, this is what we are evaluating. Okay, so basically this is being evaluated at k equal to n by 2. That's the expression. So the right hand side expression, if you write down, is n equal to 0 through n minus 1. Look at what is Wn raised to the power of n by 2 power n. This is nothing but e power minus j 2 pi by n by 2 raised to the multiplied by n. So we have n and n which will cancel, 2 and 2 that will cancel. So what we will have is e power minus j n pi. That is nothing but minus 1 raised to the power n. So we now have an expression which is minus 1 raised to the power n x of n. So it is a summation of all the terms except that the sign will now alternate, and this is equal to x of n by 2. Okay, so and this is the explanation that we have. So along the same lines, please verify that the following result is also true. The inverse transformation, the x of n by 2 value sample is equal to 1 by n summation k equal to 0 through n minus 1 raised to the power k x of k. The summation, but with alternating signs. Again, these are interesting properties that you can easily verify. Now, here are a set of additional properties that I would like you to be able to verify, and then so here is property number 5. Okay, please verify. Just now we verified the Wn raised to the power n by 2. This is equal to minus 1. That's a property that we have just now verified. Okay, number 6, Wn n by 4, that will be equal to minus j. Property number 7, Wn 3n by 4. Just substitute expression for w and verify. This will be equal to plus j. Okay. Then number 8, property number 8. We will. I would like you to verify this just by substituting the results. W subscript n up exponent k plus n. Okay, what happens if you add n to it? Again, you will find that the W coefficient, it represents a sinusoid. So therefore, there will be periodicity. So this is Wn, this is the same as Wnk. Number 9, what is Wn k plus n by 2? Again, you should substitute and verify that this is nothing but minus Wnk. Okay, how these things simplify. So within this DFT matrix, they look like all different coefficients, but that is not true because you see all these relationships that are present inside of the DFT matrix. Okay, property number 10. Wn k times 2. Okay, this is nothing but, you can write it as W of n by 2 of a different DFT matrix which is of size n by 2 times k. Okay, just a direct substitution you can easily verify. Okay, property number 11. We're getting close to the end. Wn conjugate. If you conjugate this this value, the exponent will become negative, right? And this you can write as Wn n minus 1. You can also write it as Wn minus 1. Okay, the Wn raised to the power 1 conjugate will be Wn minus 1, or you can write it as Wn n minus 1. Okay, in the same manner, again a closely related relationship, Wn raised to the power m conjugated. Okay, this is the same as Wn, W uppercase n is the subscript, the angle becomes minus m. This can be written as Wn n minus m, because n raised to the power uppercase n is always equal to 1. This relationship holds. Okay. And another aspect that you can verify is number 13, which is W subscript n mk conjugate. Okay, this is the same as Wn minus mk. Basically, the exponent has become negative, and we can relate this to Wn n minus m times k, because basically this will give you exactly the same expression. And last 14, I would like you to verify the Wn k plus n by 2 times n. Okay, so this is nothing but Wn n by 2 we know is equal to minus 1 raised to the power n Wn k. Okay, n. Okay, so basically the DFT matrix, what you find is that there are a lot of symmetries. There are a lot of similarities. I mean, there's one coefficient, it's negative. Another coefficient multiplied by j, multiplied by minus j. We find that there is a lot of what you call symmetries within this matrix. And this precisely is what we will exploit to derive the fast Fourier transform. Basically, instead of treating them all as independent coefficients on this matrix, we want to find out certain patterns, certain symmetries, which are very, very helpful to us. Now, want you to also capture the essential properties, the symmetry properties that are present in a DFT relationship, and that is something that is useful, and it'll be helpful for us to capture. Okay, so let us quickly look at the symmetry properties, because then that will help us to understand the table that is present here. So the first symmetry property that we want to understand, let us look at properties number 9 and 10. Okay, we have, let me insert a page. Okay, so properties number 9 and 10. Property number 9. Okay, so if you have the expression x of k is equal to summation n equal to 0 through n minus 1 x of n wn n kn. Okay, and what we want is we look at the corresponding DFS. X tilde of k is equal to summation n equal to 0 through n minus 1 of x tilde of n w n k n. Okay. Now remember the way we derived the symmetry relationships. Conjugate on the left hand side, you have to conjugate all the terms on the other side. So you will get x conjugate of n and x and so the first relationship that we have for the DFS is that x tilde of n has got a relationship DFT coefficient, which is given by, do one more step, x tilde conjugate, replace k with minus k, then what you get will be n equal to 0 through n minus 1 x tilde conjugate of n wn kn. Okay, so we know that x conjugate of n has got a DFS relationship, which is given by x tilde conjugate of minus k. Okay, now exactly the same relationship we want to leverage for the DFT. Then in that case, what we get is x conjugate of n will have a DFT coefficient, which is given by x conjugate, minus k will go outside the range 0 to n minus 1. So you interpret this as modulo n, minus k modulo n. So that is what we have in terms of the property number 9. We can tick off property number 9. Again, it's a direct relationship. Similarly, we have one more property that we use for the symmetry relationships, which is you replace or represent x tilde of n equal to 1 over n summation n k equal to 0 through n minus 1, 0 through n minus 1 x tilde of k w n minus k n. Okay, that is the relationship that we have, and I'm going to conjugate it, conjugate all the terms, and this will become a plus sign, and then replace n with minus n. So then we get x tilde conjugate of minus n is equal to 1 by n summation k equal to 0 through n minus 1 x tilde conjugate of k wn minus kn, and that gives us the relationship that x conjugate tilde conjugate of minus n has got a DFS relationship, which is given by x tilde conjugate of k, and this now is going to give us the DFT coefficients, which are going to be derived from the corresponding DFS relationship. So this is going to be x conjugate minus n will go outside the range, so we will interpret minus n modulo n, and this will be the DFT relationship which is given by x conjugate of k. Okay, so we have two relationships, that is, if x of n has got a DFT relationship given by x of k, x conjugate of n has got a DFT relationship which is given by x conjugate of minus k modulo n, and x conjugate of minus n modulo n has got the DFT relationship which is given by x conjugate of k. Okay, these are the three foundational results that we need for the symmetry properties that we will be deriving. Okay, so let me once again go back and make sure that you are comfortable with the two relationships that we have obtained. Again, we have used the corresponding relationship from the DFS, and then wherever the index was going outside the range, we have interpreted it as modulo n.